Okay, the rubber band car practice quiz. First off, I want to say that number 2 is a little bit too, I don't know, it's just kind of weird. I'm going to explain it, but I'm not going to put it on the quiz unless it's going to be an extra credit problem. So, starting in order. This is all the information you get. This first part, I divided it into 3 parts. I guess the first part's basic stuff relating to a lot of the kinds of problems we've already done. The middle part is relating to a video analysis. You're given a frame rate of a video, and you're given the number of frames it takes this car to cross a floor tile. Third part, this is testing friction, and hopefully we will do that part in class tomorrow. So, question number 1. What's the maximum torque on a car's drive wheels? So in this picture, this is my solution to number 1. This is the back wheel or the drive wheel of a car. It could be the front wheel. You could have a front wheel drive. This is where the rubber band is stretching, and the rubber band is pulling to the right on this string, and this is a very enlarged axle, so just so you can see it. And the string, which is pulled by the rubber band, applies a force right at the edge of the axle. So the axle is a circle, and this string is tangent to the circle. When you have a force applied right at the edge of some circle, the torque applied by the force is the force, F, multiplied by the radius of the circle, R. So in this case, the torque caused by the rubber band is the force exerted by the rubber band multiplied by the radius of the axle. And the question asked, what's the maximum torque? So for that, we're going to use the maximum force. The rubber band, when you wind up your car, when you start to wind it up, you first hook something onto that back axle. There's not a lot of tension in the rubber band. That's this minimum force here. That's just the force to stretch it on so you can hook it on the axle. When you wind and wind and wind and get it tighter and tighter and tighter and eventually stop, that's where this maximum force comes in. Then you set the car down and you let go, and it takes off with that maximum force, creating this maximum torque, which creates another force pushing back against the road here that we'll get to in a minute. So the formula for this torque on the wheel and axle is force times radius. Since the rubber band is pulling on the axle and not, it's pulling on the edge of the axle, not on the edge of the wheel, you use the axle radius. If you had attached the string right here, then you'd use the wheel radius, but the force is being applied at this radius, not at that radius. So maximum torque is the maximum rubber band force, 35 newtons from the table, multiplied by the axle radius, and you get newtons times meters. The units are 0.07 newton dot meters. You can call it just newton meters. Number 2, I think I'm going to skip for now, just because I want this to flow a little bit. So number 1 gives us it gives us a torque. Torque is like a force, but it's not really a force. It's a force times a radius. And that twisting, you can think of it as a twisting force, is transmitted to the edge of the wheel. It starts with the string pulling the axle, but by doing that, it spins this whole wheel and axle thing around, and it transmits a force to the edge of the wheel. It's the same torque throughout. This thing starts the torque, but then the torque gets transferred and creates a force here. We're going to number 3. I've made one of those little triangles to manipulate the torque formula. It's usually torque equals force times radius. You can solve for force instead of solving for torque. So the force equals torque over radius. What force am I talking about? I'm talking about this force now. When we've got a torque on this wheel and axle, which we already calculated, that torque creates a force right here where the wheel touches the road, and the force is pushing the road backward. And the radius corresponding to that force is not the axle radius anymore, it's this radius from the center of the wheel to the edge of the wheel. So now we're going to have a bigger radius and the same torque, which means we're going to have a smaller force. So I'm going to take this torque, substitute it in here, and I'm going to put in the wheel radius, and then that'll tell us what the force is exerted at the edge of the wheel. There's the torque from number 1 divided by the radius of the wheel, 0.08, and that gives us the force exerted at the edge of the wheel, 0.875 newtons. Now notice, if you look at these numbers, 35 newtons, that's how much, that was this rubber band force. This force is 0.875 newtons. It's less than 1. This is 35. The reason this force is so strong and that's so weak is that this force is multiplied by a little tiny radius to get the torque. This force is multiplied by a big radius to get the same torque. Same torque can either give you a little force and a big radius, or a big force and a little radius. The force and radius have to be multiplied together to give you the same torque. They're inversely proportional. Number 4 is asking, what's the car's mass in kilograms? That's straightforward. Divide grams by 1,000 and you'll have it. So mass in grams divided by 1,000. If you like the units to work out, you would just say 160 grams divided by this ratio of 1,000 grams per kilogram. When you divide grams over grams per kilogram, the grams cancel out and you get kilograms. But divide by 1,000. Number 5, assuming the wheels don't slip, what's the approximate maximum acceleration? So this maximum acceleration of the car, I should probably just draw a whole car here. This acceleration of this car is caused by the wheels pushing the road backward and the corresponding equal and opposite force of the road pushing the wheels forward. And it's not the front wheels, the back wheels is where this force takes place. So we calculated earlier what the maximum force was of this wheel pushing the road backward. That was in number 3 right there. So the wheels push backward with a force of 0.875 newtons, and that makes the car go forward. We just need to figure out what acceleration that's going to create. Harkening back to Newton's second law, F equals ma, we can do the little triangle thing or do some algebra. And if we're looking for acceleration, acceleration is just force divided by mass. So if we know this is the force with which the wheels are pushing, and therefore with which the car is being pushed at its maximum, then we put in that maximum force divided by the mass of the car, and we'll get the acceleration of the car at its maximum. So that's what I've done here. The acceleration equals the maximum force of the wheels pushing the road backward divided by the car mass. This is the maximum force of the wheels. This is the car mass. 0.875 divided by 0.16 is 5.47 meters per second squared. Pretty fast acceleration. Just going to check and make sure this camera is still running. Yep. Think so. I'll do maybe one more and then I'll make a new video. Number 6. What's the average force required to stretch the rubber bands? Like I mentioned earlier, when you start to pull on these rubber bands, when you pull them backward just in the beginning, you begin to pull, it's pretty easy. It gets harder and harder and harder. So this is the minimum force just to take this string and hook it onto the back axle. It's 5. And then when it's fully wound, it's 35. So you just average those two forces, add them together and divide by 2. There's number 6, average force, minimum force plus maximum force over 2, 35 plus 5 divided by 2, get 20 newtons. And I think I'll stop there.